Welcome to CS 101, Modeling in MATLAB, Lecture 27, on curve fitting and modeling using MATLAB. Today's kind of one of our capstone lectures. What we've examined coming through this course is how to build various kinds of scientific models. Today we'll be applying that to building specific equations that try and model data sets. We're going to start by doing that using polynomials. We're going to distinguish this kind of curve fitting and linear fitting from interpolation. We're going to try and understand its limitations, and then we're going to talk about some other options you have for trying to fit and model data progressively. Fitting, or regression, describes the technique of creating equations, which are normally polynomials, to model or predict behavior given some recorded data set or observations. We move from the set of data through the creation of an underlying equation with appropriate coefficients to a functioning predictive model. Ideally, we also know something about the expected error, that we have a way to assess that. Now here what I've done is I've created a set of points x using linspace. I've created a set of points y, which is a parabola based on x and has some random noise added into it, so it's a little bit wobbly like a real observation would be. If I plot x and y as blue circles, then you can see here that we end up with something that's almost a parabola, but because of that noise I added in, it has the wavering features that you would expect in a real measured data set. Now, what I've done here is I've used polyfit to fit x and y data to a second order polynomial, to a quadratic polynomial, and it produces the coefficients that best fit that polynomial. So here we have x squared, 1.0245x squared, minus 1.0154x plus 0.2536. And you can compare that to the y value that's actually present up above. Next, I'll go ahead and plot these data. So I'm going to use linspace. I'm going to use polyval on my coefficients and on the data values xfit. And this gives me a curve that shows me what my fitted data look like as a model. So here I've produced the unique parabola, the unique second order polynomial that best minimizes the error from each of these data points. So this is what modeling generally is going to mean. It means we take our observations, we take our data points, here are the red circles, and we apply some kind of mathematical technique behind the scenes. Typically this is hidden to us at this point. It lives in polyfit or spline or a different function like that. And it finds the unique polynomial that best accommodates all of our data with the minimum amount of error. Error here being defined as the difference between one particular value and the curve at that point. You should go ahead and try changing the value of n in polyfit to see how the fit is affected. An n of 1 would be a linear fit, an n of 3 would be a cubic fit, and n of 5 would be a quintic or fifth order fit. Here, we're going to use a higher order polynomial to fit our data set. This is a new data set that I've generated. And I've produced this, and you can see that over the range 0 to 1, I'm actually getting a perfect fit along these values here, using this 10th order polynomial. Now in practice, this is what we would call overfitting, right? We're actually hitting every single point here, but we're doing it at the price of introducing some wobbling or wavering in the middle of this field here. So let's try that with a cubic polynomial. And here you can see a cubic. It doesn't quite hit all of the points, but it's a nicer, smoother representation overall. It doesn't introduce that wobbling that the 10th order polynomial started to introduce. Equations that are more complicated than a polynomial fit do exist. So you could fit something with an exponential form, or you could fit something like a Gaussian, like e to the negative x squared. It gets more complicated because you frequently have to transform your data by taking a logarithm or a root or something like that to get them in the form that you want before you try and fit the curve to it. So it requires a little bit of finesse, and you'll typically need a theoretical reason to expect such a form. So for the most part, fitting things with polynomials or maybe with splines, which are a special type we'll examine in a moment, is the best way to handle these situations. When we estimate the error of a fit, we need a unique way to do this. We don't want to just take the difference between our model and a particular point, because if some points are above our model and other points are below, the positive and negative values in error might cancel each other out. And so you could actually have quite a bit of error, but it would look like your error was close to zero because of equal amounts of error on both sides. So instead, we need to calculate our error based on a quantity that's always positive. We're going to use something called the L squared metric, which means we take each known value of y and we subtract the corresponding fitted value of y and square it. Because it's squared and it's a real number inside, this value is always positive, and it should be close to zero. And we're going to have this bit left over called the residual, which represents the difference between our fit and the value we're looking at. Now, the values that we're going to be looking at should be close to zero, and what that means will change depending on the situation that you're in. So it's something that you just have to get a feel for by comparing several different models and figuring out what's going on as you examine those. So here we can see for this random data set, again, we fit a cubic polynomial, third order polynomial through the data. And there's a lot of scatter because this is not really a cubic behaving data set here. So our error, which is this sum of the absolute values of the difference squared, is 0.79. Which is pretty high, and if we look at this plot, we can see why. It's because most of these points aren't actually well fit by this particular curve. If we were to pick a different curve, we might be able to do better than that. So we can think about error in a couple of different ways. We can think about it as the difference between known points or observations and the model. So the difference between our known values and the modeled values, and that's our residual. Or we can think about it the difference between a known curve and the model. So if we know what the data are supposed to behave like, for instance, using something like Ohm's law, then we can check our model's fit against that analytical curve that already exists. Curve fitting in modeling, like optimization, is a deep and varied field that has a lot of different applications depending on the area that you're in. There's also a lot of ways to describe the goodness of fit, or in other words, the opposite of the error. There's a lot of ways to try and capture all the data, and there's a lot of ways to deceive yourself, for instance, by overfitting.